Hello everyone, and welcome back. Today we're covering the second law of thermodynamics. This is the law that tells us that not every energy-conserving process is actually allowed to happen. Heat flows from hot to cold, and never the reverse. A gas spreads out to fill a room, but never spontaneously collapses into a corner of that room. So, nothing about energy conservation really forbids these in reverse. But the second law is what explains why they still never happen. And the key idea of it is entropy, which is a term you might have heard of before. And there are two ways to think about it. The first comes from heat and temperature. It turns out that heat divided by temperature behaves like a genuine fixed property of a system, unlike heat alone. And using that, you can show that this quantity always increases for any real process. The second comes from probability. Entropy also measures how many microscopic arrangements are consistent with what a system looks like from the outside. So a spread out gas has vastly more ways of being arranged than a clumped up one, and systems naturally drift towards whichever state has more of these arrangements available. Increasing entropy and increasing disorder turn out to be the exact same idea, but they just reach from two completely different directions. So together this gives us the second law. The total entropy of an isolated system can never decrease. Now this is how we would usually write it. So the second law, the change in S, which is entropy, is greater than or equal to 0 at all times. And for a specific system, exchanging heat with a reservoir at a temperature of T, we can write this as ds equals changing Q reversible over temperature, and therefore the change in entropy is equal to the integral of the change in Q reversible over T. And the reason why we write reversible specifically is because only in a reversible process, which is one that we can reverse the whole thing and end up with the original state, does the system have one well-defined temperature to divide the heat by. So let's move on to some questions. Question 1. This states that a block absorbs 600 joules of heat reversibly from a large reservoir at a constant temperature of 300 Kelvin. So Q is plus 600 joules as it is absorbing the heat, and temperature is equal to 300 Kelvin, that's given. Calculate the change in entropy of the block. So we can simply just use this equation that we have written here earlier. So let's sub these numbers in. Joules over 300 Kelvin, and that gives us a change in entropy of 2 joules per Kelvin. Perfect, pretty simple. Question 2. A hot reservoir at T hot equals 400 Kelvin transfers 1000 joules of heat directly to a cold reservoir at T cold is equal to 250 Kelvin. So TH is equal to 400 Kelvin, and that means that QH equals minus 1000 joules since it's transferring heat, and TC equals 250 Kelvin with the heat of the cold reservoir being plus 1000 joules as it must be absorbing this heat that's been transferred from the other reservoir. So calculate the entropy change of the hot reservoir, the cold reservoir, and the total entropy change of the universe, and comment on whether this process is consistent with the second law. I'd just like to clarify, by universe, we don't mean the literal universe with the stars and the galaxies. It's just a term meaning the system plus everything it exchanges energy with. So it's just a technical term. So what can we do here? Well, let's start by finding the change in entropy for the hot reservoir, which is equal to minus 1000 over 400. And that's equal to minus 2.5 joules per Kelvin. And let's do the same for the cold reservoir. That is plus 1000 over 250, which is equal to plus 4.0 joules per Kelvin. Okay, cool. So the total change in entropy universe would be the change in entropy for the hot system plus the change in entropy for the cold system, which would be plus 1.5 joules per Kelvin. So that's our final answer. And is this process consistent with the second law? Well, the second law states that the change in entropy of a system, it can't decrease. So this is positive, which means that we are obeying this law and the process is consistent with the second law. Okay, now let's move on to a final but slightly harder question involving Carnot engines. Now, a Carnot engine is just the most efficient engine that we could possibly create, having a change in entropy of 0 exactly. And to quantify the efficiency of this Carnot engine, we can say that the efficiency eta is equal to the work that's emitted to the heat that is inputted, and the work out would simply be the hot heat minus the cold heat, and the heat in would simply be the hot heat. And this works because we are just simply doing energy out over energy inputted, and the energy inputted is obviously the energy from the hot reservoir, and the energy that's going out will be the difference between the two reservoirs. And if we rewrite this, we can say that's equal to 1 minus QC over QH. Now, to get this in terms of temperature, we do need to use the second law of thermodynamics. So what can we say? Well, we can say that since the change in entropy is 0 for a Carnot system, minus QH over TH, since this is the transferred entropy, plus QC over TC is equal to 0. That's the total change in entropy. And what does that give? Well, QC over QH is therefore equal to TC over TH. And nabla, this efficiency, is equal to 1 minus TC over TH. So let's move on to part A. A Carnot engine operates between a hot reservoir at TH is 500 Kelvin and a cold reservoir at TC is 300 Kelvin. So if we want to calculate the maximum possible efficiency of this engine, well, we've just derived that the maximum, actually let me just write Carnot, maximum efficiency when the change in entropy equals 0 is 1 minus TC over TH. So sub the numbers in, 300 over 500, and that gives us 2/5, and that's the maximum possible efficiency. Now, let's move on to part B. If the engine absorbs 2000 joules of heat, from the hot reservoir per cycle, calculate the work output and the heat rejected to the cold reservoir. Okay, so we know that nabla is 2/5, and we know that nabla is equal to work out over Q in, which is just QH. So let's rewrite this. 2/5 is equal to the work out over 2000. So the work out is equal to 800 joules. Perfect. And what is the heat rejected to the cold reservoir? Well, if this is the workout, and this is the total heat transfer, or heat absorption, sorry, then the heat rejected is equal to 2000 minus 800, which is 1200 joules. For the last question, we need to explain using the second law why no engine operating between these two temperatures could ever exceed this efficiency. So the way we could go about this is by saying that, well, if this efficiency was exceeded, then the engine itself would produce more work than a Carnot fridge would need to pump a given amount of heat from hot to cold. And this means that actually no energy is inputted to transfer heat from a cold reservoir to a hot reservoir. And that breaks the second law because that would give a negative entropy. So yeah, that's it. Leave a comment if you want to ask any more questions, or if there's a specific kind of video that you want me to make. And thanks for watching.